Hello and welcome to Chapter 5, where we start the definite integral, which is just like an antiderivative, the opposite of taking a derivative. So we are going to be able to, at the end of this lesson, estimate the area under the curve with finite sums. This is section 5.1. We're going to do it in one video, I hope. We've been studying differential calculus, which means we take the slope of the tangent line to the curve. Integral calculus involves finding the area under the curves. What does calculus mean? This is just a little review. It means a method of calculation. All right, so our first example is a very simple one. It is a function of speed where a train is moving 150 miles per hour from 2 a.m. to 5 a.m. I'm not sure trains, except maybe in Europe, move this fast, but I know the train to Chicago goes, there's a stretch in Indiana, I think it goes about 120 miles an hour, so you should take it sometime. It's a fun, comfortable train. But anyway, you're moving at 150 miles an hour from 2 to 5. So our function looks like this. It's a straight line moving from 2 to 5. If we want to know the distance that the train travels from 2 to 5 a.m., we actually take the rate, which is 150, times the time, which is between 2 and 5, that's 3. What I'm trying to show you here is that if you take the area under this curve, this is the area under the curve of the speed, you actually get 150 times 3. Okay, so it's taking the area of a rectangle. And that is the big aha that happened with our friends Leibniz and Newton. All right, and this works so great if you have a constant speed, but no vehicle, no particle ever moves at a constant rate. So what happens when you have a rate that looks like this? You're going along, you speed up, you slow down, you stop. Okay, so how can we calculate this speed? The way we do that is using the same method, only we're going to break this area down into small rectangles. Okay, and so our rectangles are going to be estimates, which is why you always see estimating the area under a curve. Because if you take these rectangles, it's not going to be a perfect matchup. You may have an underestimation, or you may take rectangles that look like this, and therefore you're overestimating the curve, right? You're above the curve. So our estimates are going to be over or under, depending on what's happening with the curve and depending on how we make our rectangles. Also notice that the more rectangles we have, the closer we're going to get. If I make this little rectangle right here into 20, if I have 20 rectangles in there, I'm going to come pretty close to the area under that curve. Okay, so this distance here is the area under the velocity or the speed curve. We calculate this by adding the rectangles. And notice when the area under the curve is actually the integral or the distance that the vehicle or the particle travels. We are going to look at 3 ways to get rectangular approximations. And these are called RAM, the rectangular approximation method. I'll probably never use those 3 words again. I just say RAM. And this is how we're going to get rectangles from a curvy top. So there are 3 ways. We can use the midpoint rectangular approximation method. I use those words again. We can use the LRAM, left hand endpoint, or we can use the right RAM, which is the right endpoint. Okay, so these 3 curves are all increasing functions. So please note that these are increasing functions. So if I take a midpoint of this rectangle, or of this curve, I am going to get a rectangle that approximates the area under the curve fairly well. Okay, so this is the midpoint of MRAM is a pretty good, let me say okay. It's an okay way of approximating the area under the curve. If I use the left endpoint, which means the left-hand side of an increasing function, I am going to have an underestimation, right? This is going to be an underestimation. Okay, if I use the left RAM. If I use the right RAM over here, I am going to have an overestimation. All right, this is important because you are always asked this on the AP exam. They will ask you whether it's an overestimation or underestimation, and you have to look and see if it's an increasing function or decreasing. Okay, these are the three examples for increasing. For a decreasing function, it's basically the opposite. All right, a midpoint, again, gives you an okay estimation. All right, a left RAM, in this case, it gives you an overestimation because your function is decreasing. And the right RAM gives you an underestimation because you're going to give the area of that rectangle, and therefore it underestimates the area under the curve. We are going to look at a real problem. This is page 270, number 4, and we're going to estimate this using the three different methods: left RAM, right RAM, and midpoint RAM. Also, please notice that in your book is going to give a lot of information. Please read your book. I know it's not a perfect book because it's a college level book and it expects you to, I don't know, understand a lot of things that it doesn't tell you. But anyway, we are going to try to read the book and figure out what it means. Okay, so anyway, all right, the particle starts at 0, moves along the x-axis with a velocity of t squared plus 1. That is this blue function that is graphed here, t squared plus 1, for time t greater than 0. These are important things that they're telling us. Where is the particle at t equals 5? So what we want to do is estimate the area of the curve under here between 0 and 5. And that is really the area going from 0 to 5, and also bound on the bottom by the y-axis. Okay, so we're going to use 5 rectangles. All right, so that is our interval. Our interval equals 5, and you will see that word often where it tells you how many intervals. And that makes a difference how we calculate our 5 rectangles. So we have rectangle 1, 2, 3, 4, 5. This is going to be the left RAM method. Here is my left endpoint. There is my first rectangle. Here is my left endpoint. This is my second rectangle. Here is my left endpoint. This is my third. My left endpoint, my fourth, and voila, my fifth endpoint. Left RAM is going to give us an underestimation of this curve because it is increasing. And you can see that just from drawing the picture. All right, but we're still going to calculate. All right, so the first rectangle, the height of that rectangle, remember the area of each of our triangles is the function value times the change in the x value. The change in the x value is 1, right? The width of each, I'm sorry, it's not a 2. The width of each rectangle is a 1. Okay, so our delta x is always 1. Our function depends on what the x value is. So when we calculate the area of these 5 rectangles, rectangle number 1 is the function at 1 times 1. The rectangle number 2 is the function at 2 times 1, because the width is 1. Okay, the height of rectangle 3 right here is, oops. Let me start that again, sorry. I should be doing the function at 0, right? This right here, endpoint, or the left RAM point right here is f at 0 times, the width is 1, f at 1 times 1, plus, we're going to add each of these. Okay, this is the area of rectangle 1, rectangle 2. The area of rectangle 3 is the function at 2 times 1. The area of rectangle 4 is the function at 3 times 1. And the area of rectangle 5 is the function at 4 times a 1. All right, this gives the height times the width of every single one of those 5 rectangles. All right, so if we calculate this, remember our function is v times change in x, or change in t. I guess we should say if we're going to be really cool about this. All right, so the function at 0 is 1. So the area of this is 1 times 1 plus the function at 1. If I plug a 1 into t squared plus 1, I get 2. So 2 times 1. The function at 2 is 4 plus 1. That's 5 times 1. The function at 3 is 9 plus 1. And the function at 4 is 16 plus 1, or 17. These 5 areas added together gives you 35. This is the particle's position at t equals 5. Okay, that gives the area under the curve. All right, the next one is using right RAM. So let's go ahead and again draw our rectangles. Okay, so rectangles. Here's our rectangle at 2. Now notice, right RAM for an increasing function is going to give us an overestimation because this is an increasing curve. Okay, so these are 4 points, or 5 points. Okay, this is because it's an increasing function. Right RAM is an overestimation. All right, the function is the same, t squared plus 1, but our points are different. So the area for right RAM equals the velocity curve times the change in the time. Change in time, again, is always 1 because it asks us to do 5 intervals again. So each of our intervals equals 1. Okay, so area is the function at 1 times 1 plus the function at 2 times 1 plus the function at 3 times 1 plus the function at 4 times 1 plus the last rectangle is the function at 5 times 1. It might look a little redundant that I'm writing 1 every time, but your interval is not always equal to 1. It can be something else, which you will see. Okay, the function at 1. Plug in a 1 here, and we can kind of use some of the information from our last problem also. So 1, this one is 2 times 1 plus, function at 2 is 5, function at 3 is 10, function at 4 is 16. Function at 5 is 26. So we said this would be an overestimation, should be bigger than the last one, and it is. It's actually equal to 60. That is the estimation for right RAM. Okay, we have one more, and that is the estimation at midpoint RAM. let's draw our rectangles again. Here's our midpoint. And, to draw that, but I do like to do this because our midpoint is actually at 1/2. This midpoint right here is at the point 3/2. This is at 5/2. And therefore, our calculations use fractions. Yay. And we really can't tell if this is an overestimation or an underestimation. So we just have to use what we have here. All right, so it is an increasing curve, but remember I said MRAM is an okay estimation. So we're going to do the same thing we did with the other two approximation methods, except now we're going to take the function at 1/2 times 1 plus the function at 3/2 times 1 plus the function at 5/2 times 1, because that's the actual point where we touch the curve, is in between all of these. The function at 7/2 times 1 plus the function at 9/2 times 1. All right, so you'll have to trust me. Actually, no, you can check your answer. If you, or check this answer, you should get 46.25. All right, and that should be your estimation using MRAM. All right, we're going to do more of these in class. And please read your book. That is section 5.1, the beginning of integrals.